for the session. Okay, so welcome everyone to a new young session within our machine learning needs mathematical optimization online seminars. We are pleased to be back and to see many participants. As always, we are going to have 3 speakers and all the questions will be asked at the end, but if you have some urgent matter, you can write it in the chat. Our first speaker is Caroline Spieckermann from Technical University of Munich, and she is going to talk about a graph neural network-based reduced then optimized heuristic for the fixed charge transportation problem. So I'm going to share the presentation and it is all yours.
All right, thank you, Nuria. I hope you can all hear me well. Okay, I hope that you can see the slide. So, hello from my side. So I'm Caroline Spieckermann. I'm currently a PhD student at the Technical University of Munich, and I'm very happy to present one of my research projects at the intersection of operations research and machine learning today. So we will be looking at the fixed charge transportation problem, which is an NP-hard problem, and we will use machine learning to predict a relevant subset of variables. So we will hopefully get a smaller problem, which hopefully is easier to solve. So this is joint work with my 2 supervisors, Professor Stefan Minner and Professor Maximilian Schiffer, both from the Technical University of Munich. So the situation in the fixed charge transportation problem is the following. We have supply nodes with certain capacities, and we have demand nodes with certain demands. And now we are looking for a cost minimal assignment of supply to demand. So we have 2 types of costs. We have variable costs, which apply for every unit that is shipped, and we have fixed costs, which apply as soon as we use a certain connection. And while the problem is easy to describe, it is not so easy to solve because the fixed charges make the problem NP-hard. This is a bit unfortunate because the FTTP can be used for a wide range of applications, not only transportation in the strict sense, but also more general assignment problems that have this kind of structure. So we were wondering whether we could train a machine learning model to predict a relevant subset of edges, so we would get a smaller problem, which might then be easier to solve. So here you can see the pipeline in more detail. The input is the original FTTP instance. We then use a machine learning model to predict for each edge the probability of being part of the optimal solution. Based on these probabilities, we then select a subset of edges. There's one caveat here, so our machine learning model doesn't know anything about constraint optimization, so there's no guarantee that the predicted edges actually give us a feasible problem. So what we do is we run a fast and simple greedy heuristic and add the solution edges to a subset of edges. This way we can guarantee that the reduced problem is actually feasible. And we can then use any suitable solver. It can be heuristic or exact to solve the reduced instance and get a solution for the overall problem. Now here you have an illustration for an exemplary instance. So the machine learning model will give us, for each edge, the probability of being part of the optimal solution. We generate a reduced edge set and get a solution. And hopefully this solution is not too far from the optimum. So there's no guarantee for optimality. So just to be clear about that, once we reduce the edge set, we cannot guarantee optimality anymore. But that's okay. I mean, if the exact algorithms don't scale to large instances, or we have to rely on a heuristic anyway, well, then good is everything we can hope for anyway. So to get at least a good solution, we need to have a good predictor. And we decided to use graph neural networks and train them with supervised learning. So let's have a look at the training pipeline first. What we do is we generate a sufficiently large data set of small training instances. So it's important that these training instances are small because we then solve them to optimality and record the optimal solutions. So this gives us instance solution pairs. We then treat the learning problem as a binary classification task. So for each edge, we want to predict whether or not it is part of the optimal solution, and we minimize the binary cross-entropy loss. Before I get to the model architecture, I want to briefly summarize the, let's say, criteria that a machine learning model has to fulfill to serve our purposes. First, it should be size agnostic, because we want to be able to train on small instances and then apply it to larger, like hard instances. It should also be permutation invariant, which means that the order of nodes should not matter, because our supply and demand nodes do not have a natural order. We want to avoid feature engineering as much as possible, and the model should be parameter efficient. And of course, it should also be good. So this is how our model looks like on a very high level. So we have three sets of objects. We have supply nodes, we have demand nodes, and we have edges. The inputs are just the raw instance features. So for the supply nodes, it's just the supply quantity. For the demand nodes, it's the demand quantity. And for the edges, it's the variable and the fixed cost. And then we use convolutional layers to share and combine information. So for example, looking at supply nodes, we would take the supply node feature vector from the previous layer and combine it with feature vectors of the incoming edges. And we do this over multiple layers. And with each layer, the objects gain a better, let's say, understanding of their embedding in the overall problem. In the end, we are interested in the edges. So after some convolutional layers, we take the edge feature vectors, pass them through some additional dense layers, and make a prediction. We use a logistic activation function, which will then give us a value between 0 and 1, which can be interpreted as the probability of being part of the optimal solution. Now, before we get to the numerical study, let's just have a very quick look into the literature, not too much because of time, but we basically build upon two streams of research. So on the one hand, we have the literature on FCTP algorithm, and then we have research on machine learning for combinatorial optimization. So there have been several exact and heuristic algorithms for the FCTP. The problem is that the exact algorithms do not scale to large instances, and the heuristics also do not perform very well on large instances. So there is still a need for an efficient and good algorithm for the FCTP. Then on the other hand, we build upon previous work on machine learning for combinatorial optimization. I don't think do I have a pointer here? I don't know. So the last paper that you see here on the list is the one that is most related to our work. So the two papers by Sun and co-authors, because they also use machine learning to predict a relevant subset of variables, but they consider different application, different problems, and they also do not use graph neural networks, but a support vector machine, which then relies on certain statistical features, which are quite expensive to compute, and at least for our case, did not perform very well. So that's also a bit different from what we do. In our numerical study, we consider different types of FCTPs in terms of their parameter distribution. So for example, we look at instances which have a high variability in the demand and supply quantities, and others which have a low one. We consider different ratios of variable to fixed cost. We consider different structures like random cost, or more structured like in the Euclidean space. And we also distinguish between balanced and unbalanced instances. So a balanced instance is when total supply is equal to total demand, whereas in unbalanced instances, we assume that there's some surplus of supply. We train our models on 4,000 instances and do the benchmarking on a separate set of instances with 30 instances for each configuration of interest. As I said, we only train on small instances, but we do evaluate on larger instances with up to 120 supply and demand nodes. And we consider three different solvers. So we use Gurobi as an exact MIP solver, and also consider two common meteor heuristics for the FCTP, one taboo search algorithm and one evolutionary algorithm. Now let's take a look at the results. So first, let's look at the pipeline with an exact solver. So these are the results for small instances. Of course, the runtimes for small instances are so low that for most practical applications, there would be no need for speed up. But this is the instance size we trained on. So looking at small instances will give us a first indication on how good our predictions actually are. So on the x-axis, you can see the relative size of the problem. 1 would mean that we include the full edge set. 0.5, for example, would mean that we include 50% of the edges. The green line is the runtime, and the blue and the orange lines are the mean and median optimality gaps. And what you can see is when you decrease the edge set, then runtimes go down. And as long as you don't reduce the edge set too much, the optimality gaps remain very low, like below 1%. So for example, with an edge set of 35% of the edges, you get a very good compromise between runtime and solution quality. Now let's look at larger instances. So remember, we only train on small instances. So now looking at larger instances will show us how well our model generalizes to larger instances. And actually, the results are very similar. So we still get a very good trade-off between runtime and solution quality when we apply the problem reduction. To provide a few more insights into how the problem reduction actually helps the MIP solver, I have plotted the development of the lower and upper bounds for the full problem and for the reduced problem for 2 exemplary instances. So these are just 2 randomly selected instances, but the pattern is quite stable and the reason for the result that we see above. And what you can see is that the problem reduction helps both with like the faster conversion of the lower bound and the upper bound. And the faster conversion of the upper bound is particularly interesting because it means that when runtime is limited, then solving the reduced problem will oftentimes give you a better solution than solving the original problem. And this, of course, comes in handy when you want to solve large instances. Then the problem reduction can really help you narrow down the search space on promising regions. Now let's look at heuristic solvers. For heuristic solvers, the story is a bit different. So for an exact solver with unlimited runtime, reducing the edge set can only make the solution worse. But for heuristic solvers, it can actually be different. So heuristic solvers can actually benefit from the problem reduction. And that is exactly what we can see here. So again, the x-axis gives you the relative size of the problem. And the 2-meter heuristics do not perform best for the full edge set, but actually for edge sets around like 40–50%, like for this example, like for this problem size. So yeah, so this shows like heuristic solvers actually benefit from the problem reduction, and also they do not provide. Does not only provide a better solution in the end, but it also helps with the convergence. So again, you can see here the best solution found so far over the number of iterations for the full problem and the reduced problem. And as you can see here, the reduced problem does not only give you a better solution in the end, but it also gives you good solutions much earlier. We have evaluated our pipeline. So the results I have presented so far are all like on some kind of base configuration. But we also wanted to consider different types of FTTPs to see how the different distribution of parameters affect like solver runtimes and also edge predictability. What you can see here are the Gurobi runtimes for different types of FTTPs. So B50 means that we sample from a larger value range when sampling supply and demand quantities. We consider different variable fixed cost ratios, different cost structures, and different degrees of balancedness. The main takeaway is that the parameters do have an impact on the Gurobi runtime. So for example, B50 has significantly larger runtimes than the base configuration, for example. On the other hand, as soon as you have some unbalancedness, so some surplus of supply, runtimes go down. But what's interesting now is that despite these differences in runtime, the quality of our prediction is very stable. So it's very similar for the different problem types if you look at the optimality gaps. The only attribute that had significant impact on both the runtime and the optimality gaps is unbalancedness. So as soon as you have some surplus of supply, both runtimes go down and optimality gaps. So the additional flexibility by having more supply makes the problem easier to solve and easier to predict, which is kind of intuitive, I would say. Now, to wrap it up, I have shown you how you can use graph neural networks to predict a relevant subset of edges for the fixed charge transportation problem, which gives you a smaller problem that is easier to solve. We considered different types of FCTPs and also considered generalization to larger FCTPs. And we see several directions for future research. First, you could consider alternative learning tasks and machine learning models. So at the moment, we treat it as a binary classification task, but there might be other options. You could also take like the same model, but embed it into a different type of pipeline. For example, use it with an exact algorithm or use it in some kind of end-to-end learning way to directly predict a solution. And last but not least, you could take the whole thing and just apply it to a different problem class and see how it performs. So that's it. Thank you for listening, and I'm happy to take your questions later.
Okay, thank you, Caroline. It was very interesting, and we had a few questions, but we are going to place them at the end, okay? So now it is the turn of Miaolan from Cornell University, and she's going to talk about a reliable, adaptive, stochastic optimization with high probability guarantees. So it's all yours. You can share your screen.
Okay, thank you. Let me share my screen. I think it's this one. Okay, yeah, thanks for having me. So yeah, I'll be talking about reliable adaptive stochastic optimization for messy data. And this is a joint work with Billy Jean and my advisor, Katia Scheinberg. Okay, so we know that real-world problem or real-world data is kind of messy. We have all different kind of issues in those data. We can have bias, noise, or even corruption in our data. So for example, bias, we can have measurement errors or distribution shifts in machine learning. And noise could come from insufficient sampling and can also come from outliers in the data. And corruptions in data could come from like system failures or even like other adversarial attacks. So we want to kind of be able to deal with all of these issues when we work on stochastic optimization problems. So we are interested in solving the unconstrained optimization problem, say minimizing a function phi of x that is possibly a non-convex function. So in our setting, we do not assume we have accurate access to the function value or gradient. Instead, we assume that we can query some sort of oracles to estimate the function value or the gradient. So this captures many interesting settings in, for example, expected loss minimization problem in machine learning, or in derivative-free optimization or simulation optimization. So for example, in expected loss minimization in machine learning, we do not have access to the true gradient, or maybe it's too expensive to calculate the entire gradient. But what people usually do is they take a randomized mini batch and then do an average on over the mini batch to get an estimate of the stochastic gradient. And one specific issue we want to deal with is that we want to have kind of the notion of adaptivity in the optimization. So if we look at this plot, this is Adam algorithm trained on the MNIST data set. And we can see that depending on how we choose the learning rate or the step size parameter for the Adam algorithm, the performance kind of varies drastically dependent on the step size. And so in practice, this is a big issue because that means if we want to have good performance guarantees, then we will need to manually kind of tune the step size or learning rate. And this is a very tedious process and very time consuming as well. So we will like to have an algorithm that is kind of adaptive in a sense it will tune itself, tune the step size from iteration to iteration automatically. Okay, so ideally, so this is what we want. First, we want to be able to deal with messy data. So that means we want minimal assumptions on our input related to the function value to the algorithm. And second, we want the algorithm to be entirely adaptive from iteration to iteration. And of course, we also want the algorithm to be converging fast. And yeah, we also want the algorithm to have guarantees for this convergence, not only in expectation, but in high probability. So these are the things we want for our work. And there are actually quite many works in this area already. So there are a line of work on stochastic line search or stochastic step search method. And there's also stochastic trust region methods, stochastic cubic regularized Newton method. There are also all of these works are trying to tackle these issues. And in our work, what we did is that we provide a kind of unifying framework. First is to have high probability iteration results under assumptions that kind of can deal with messy data. What does that mean? It's like in previous works in the literature, usually people study the iteration complexity, but only in expectation. And also usually the requirement for the function value estimates is pretty stringent. Say, for example, many works assume function value error or noise is only bounded in every iteration. So in one of our work, we kind of extend this assumption to allow the function value estimates to be to have the error to be unbounded. As long as it follows a light tail distribution. And we also show that the iteration complexity can be not only in expectation, but also in overwhelmingly high probability. And another work we did is for unifying the framework and analysis to obtain the first sample complexity results for all of these works. Okay, so before introducing the algorithm framework, I just want to introduce the notion of oracles. So in our framework, we can think of, we have essentially two entities. One is for, one is the oracles and the other is the algorithms. So the oracles basically provide the input related to the functions to the algorithms. And the algorithm is agnostic to what oracles actually behaves internally. So for example, our zeroth order oracle provides function value estimates to our algorithm, and first order oracle will provide gradient estimates to the stochastic optimization algorithm. And we want the oracles to be relatively weak, the assumptions. So we are able to deal with these four conditions. First, the oracles, of course, it can accommodate exact function values, also biased function value in terms of the we have bounded noise in the function value estimates. It can also be unbounded noise as long as the function value estimates has the errors follows a light tail distribution. It could also be like corrupted in a sense that if you have a fixed corruption budget over the entire horizon. And the oracles for the first order oracle is kind of similar. It can deal with exact gradient. It can deal with bounded noise it can even deal with unbounded noise or arbitrarily bad corrupted errors in the function value estimate, as long as in each iteration, this error probability is bounded within less than half. So let's maybe just illustrate it. So here are two examples we see in the literature. So basically what it says is that, so here is the function and here is the point. We want to estimate gradient. This is the true gradient. And this basically says, let's say our delta is 0.3. This basically says, as long as I have 70% of the time, my gradient estimates is in the right ballpark. Say the first order oracle can give me an estimate that goes in this direction. So that is totally okay. Even with 30% of the time, my gradient estimate can be arbitrarily wrong. So this is a very weak oracle settings. So here is our algorithm framework. So let's just also illustrate this. So what this algorithm framework is doing. Basically, it says, so I'm currently at this point. First, what I do is I construct a model, a stochastic model using the probabilistic oracles I have. For example, my probabilistic first order oracle. So this is essentially the right model to have, the right local model to have at this point. But we know that with 30% of the time, our first order oracle or the gradient estimate can be totally wrong. So it's possible that the oracle will give me a wrong gradient estimate that make me to construct a model that is totally wrong. So for example, like this. And then my algorithm is agnostic to whether the model is right or wrong. It will just try to kind of take a step according to this local model. So according to this local model, we should take a step like this and move to this point. So we'll form a candidate point here. And then because we know that our first order oracle, our gradient estimate can be very wrong. So we kind of have another layer of safety by querying our zeroth order oracle to get function value estimates for the current point and the new candidate point. And if it looks like the new point is actually give me sufficient descent in the true function, in the original function, then I will take the step and I will enlarge my step size in the next iterate. So I can be more aggressive and make more progress in the next iteration. If not, I will say it's an unsuccessful iteration and I will stay at my current point and not move at all at this iteration and shrink my step size and be more conservative in the next iteration. So this is how we kind of adapt the step size from iteration to iteration according to the progress of the algorithm. So this is the idea of the algorithm framework. And this framework is very general. It kind of captures many interesting algorithms in the literature. So for example, it captures the stochastic line search method and the stochastic trust region methods. So what is different here is basically how we construct this model, the local stochastic local model, and how we kind of compute this step to take given this model. And another thing that could be different is how we choose to see whether there are sufficient enough descent compare for the original function. So so this framework gives us a way to kind of capture all these different capture all these different algorithms given these three different ways to choose different algorithms. So we can get high probability results for iteration complexities. As long as we have the oracles, the weak oracles we have seen before, we can have very nice properties for the algorithm behaviors. Essentially, the algorithm behaviors kind of give us a way to characterize them as a stochastic process. And these are the very nice properties of the stochastic process. We don't have time to go into the details of those, but given those nice properties, we can show that we can have overwhelmingly high probability, not only in expectation, but in overwhelmingly high probability for these for example, SAS algorithm, the stochastic line search method, in their iteration complexity. So this result basically says if our function phi(x), which is possibly non-convex, is bounded below and is L-smooth, then in order to find an epsilon stationary point, we can have we can bound the iteration complexity in terms of 1 over epsilon squared with overwhelmingly high probability. Note that even with exact function value information and exact gradient information, as in the classical optimization methods, the iteration bound is still on the order of 1 over epsilon squared. Okay, so one last thing I want to talk about is the sample complexity result. So we'll also be able to analyze and give a general framework for the sample complexity results in high probability. So here are the two examples we've seen before. So essentially, these are the conditions or requirements for the gradient estimates or the first order oracles. It basically says with a certain probability, we want our error in the gradient estimate to be upper bounded by these quantities. So we know that the step size alpha is also in the kind of accuracy requirement in the oracles. And that causes the key kind of difficulty because the step size kind of goes up and down from iteration to iteration. If an iteration is successful, it goes up. If an iteration is unsuccessful, it goes down. So it's kind of hard to get a hold of the step size and hard to get a hold of the accuracy requirement in those oracles. And but the accuracy requirement kind of is highly related to the sample size needed. If you need very high accuracy, you will need more samples to deliver this oracle. So the key to get our sample complexity bound is to kind of nail down what our accuracy requirement is, or in another sense is to nail down what is the behavior of the step size parameter alpha here. So given our assumptions on the oracles, as we've seen is those very weak assumptions, we can still have this very nice property, which basically is saying as long as your step size fall below a certain threshold, alpha bar, then your step size parameter basically follows a upward drift. And that kind of behavior kind of allows us to have a coupling argument between the stochastic process of the step size and a one-sided random walk. And with this leveraging on this idea of lower bounding the stochastic process of the step size using a one-sided random walk, we can have a general theorem to kind of characterize what's the sample complexity results for any algorithm that fall into this framework. As long as you have two things. First is iteration complexity in probability. And the second is what's the step size you need to have given your step size alpha is of a certain size. So it's basically a formula between your step size alpha and your sample size for the oracle. As long as you have these two things, you can essentially plug that into this theorem, and the theorem will give you the sample complexity bound for the algorithm of your choice. And that would conclude my talk, and I'll be happy to answer any question you may have.
Okay, thank you, Miaolan. It was a great presentation. And our final speaker is Quan Zhou from Imperial College of London, and she is going to talk about frontiers challenges in AI and the case of algorithmic bias in forecasting tools. So I'm going to prepare your presentation. Okay.
Yes. So hello everyone, my name is Quan. I'm a PhD student in Imperial College London, and this work follows a sequence of work with both my supervisor Yakumori Saik and Robert Schulten, and this talk focuses on the algorithmic bias in forecasting tools. Okay, let's start from a new notorious example, Compass system. And Compass, it was an AI system used by US court. It assesses the likelihood of a defendant's reoffending. In 2016, a paper in Publica found that this system is biased against African American defendant. If we look at the table, we can see that the African American defendant are almost twice as likely as Caucasian defendant to be labeled as high risk, but not actually. This system gives a score to each defendant as the predicted likelihood of a reoffending, and this score is given to judges during criminal sentences. From the figure, we can see that though there are significant differences in the score distributions between the two races. Generally speaking, AI models are not deliberately built to be unfair, and sometimes even if the model itself is innocent, the data might not be so, such that the bias sneaks in without noticing. One source of unfairness could be the underrepresentation bias. It comes from the sample size disparity directly. We know that if we are given a large dataset, we will be able to make the better prediction with less errors, but the minority subgroup normally has less data. Sample size disparities come from historical bias, such as gender roles in text and images, racial stereotypes in language. A research in 2016 used word embedding to learn from a big amount of news. It found that in that literature, men are highly related to computer programmers as women are to homemakers. And those bias in the historic dataset could be one of the reasons for the unfairness. Because when we train an AI model with the bias dataset, the model will learn all the human bias embedded. Okay, let's see how this underrepresentation bias works in prediction problems. So firstly, we look at the top of the plot. There are three gray dotted curves. They are the training data of the majority subgroup. At the bottom, there are two gray dashed curves, which belong to the minority subgroup. The minority subgroup has less data, such that it suffers from the bias. The red curve is the predicted results that focus on minimizing the overall loss. We can see that if we use the red curves, the minority subgroup experiences higher prediction errors than the majority subgroup. This is because the errors of the majority subgroup takes a larger share of the overall loss. So in order to minimize the overall loss, it's more efficient for the model to be closer to the majority subgroup. So if you wish to have the loss equalized across the subgroups, you will need to correct for the underrepresentation bias in the forecaster. The blue and the green curves show two notions of fairness in prediction that we proposed. So now we introduce this forecasting problem formally. We consider a number of individuals within a population, and this population is partitioned into subgroups. And within a subgroup, each individual is associated with a trajectory. The trajectory can be seen as a time series of observations. Then we assume the observations evolve according to a discrete time model of a linear dynamic system. We can see the two equations in this slide. The first equation is the dynamic of the hidden state phi. The second equation is the observation process of y. And G and F are compatible system matrices WMV are normally distributed process noise and observation noise with covariance matrix WMV. And suppose we are giving the observations Y of a linear dynamic system, while this system is unknown. If we can identify the system matrices to recover the linear dynamic system, then we can use this recovered system to make predictions. And it is that we propose is called proper learning of linear dynamic system. To solve this problem, we use the technology from non-commutative polynomial optimization problem, and we explain the details in the paper, in another paper. Yeah. Okay. So to address the underrepresentation bias, we propose two objectives which extend the group fairness to time series. The first is subgroup fairness. The objective seeks to equalize across all subgroups the average loss for the subgroup. The second is instantaneous fairness. The objective seeks to equalize the loss across all subgroups and all periods. Okay, and consistent with the two objectives, we propose two models that extend the fairness notions to proper learning of linear dynamic system. As shown in the subgroup fair and instant fair, the constraint describe blind linear dynamic system, and the objectives are the two fairness notions. For comparison, we use a traditional formulation that focuses on minimizing the overall loss shown in the unfair model. Okay, and then for experiments, now we assume there are only two subgroups, the advantage subgroup A and the disadvantage subgroup D. And to measure the loss of each subgroup, we use the normalized root mean square error for each subgroup. And the degree of underrepresentation bias is controlled by beta D. It is the ratio of the amount of observations in subgroup D to that of subgroup A. Okay, and then the first plot suggests how the degree of bias affects the loss of each subgroup with and without considering fairness. At each degree of bias, the quantity of loss of 5 repeated experiments for each subgroup. We will expect that loss of subgroup A to be generally lower than those of subgroup D, leaving a gap. In the plot, we do see that all boxes at the left subplot are generally higher than those boxes at the right subplot. Compared to the unfair model, our model with fairness constraints, that is subgroup fair and instant fair, show narrow gaps and higher fairness between the subgroups. Okay, we further extend our notions of fairness into the post-processing compass score. For our fairness notions, we use linear regression models with features of original compass score, period instance, and age category of each defendant. On the other hand, we use the AFAS 316 toolkit as the state-of-the-art. We also include the original compass score as the results of traditional models. And to compare the performances, we use the 3 fairness indices: independence, separation, sufficiency, and inaccuracy. And for all the performances, the smaller the better. And for the test set, we have the normal test set, and we also include a reweighted test set. Because the test sets selected from the past might not represent the future perfectly, we might expect that in the future the data will be more balanced between subgroups. So we use 4 indices on 2 test sets such that we have 8 performance indices in total. Our fairness indices are derived from the 3 types of fairness notions in statistical parity. We refer to the book Fairness in Machine Learning. If we are given a ground truth Y, prediction F, and a sensitive attribute, independence will measure how far we are from the demographic parity. Separation measures how far we are from the false positive parity and false negative parity. And sufficiency measures how far we are from the predicted rate parity. We firstly implement the state-of-the-art. We implement all the post-processing methods in the toolkit on compass dataset for 5 rounds. The left plot shows the mean value of A performance indices on the A axis. And the right plot shows the 8 performance indices of all rounds in 8 sectors. The yellow method outperformed the others because it is the closest to the origin. The method is also suggested by the author of the AFA 316 toolkit. We use the yellow method as the most powerful baseline to compare with our method. The 3 post-process methods, subgroup fair, instant fair, AS360. For 50 rounds, the outputs are compared with the original compass score. And the left plot shows the mean value of all performance indices associated with output from full models. The right plot gives the fairness matrices of all experimental rounds. And we can see that the blue model improved fairness while maintaining the same level of accuracy as the original compass score, and the yellow method also improved fairness, but at a very high expense of accuracy. Yes. Yeah, if you're interested, you please go check our paper. Okay, thank you.
Thank you very much for the great presentations. We now open up for questions from the audience. So if you have a question, please write in the chat or raise your hand. We already have a few questions from earlier for you, Caroline, in the chat. The first one being whether or not the runtime you showed include the training of the graph neural network.
No. So it's offline learning. So we train beforehand, and then assume that the model is trained.
And there's also a question of the applications of your work in supply chain management and industrial scenarios.
Yeah, I mean, right now, just like it's more on the methodological side. We use like a standard benchmark setting, but the approach is generic and could be extended to additional constraints or whatever like the industrial problem has. So there's no reason why it could not be applied, but here's a more like generalized setting.
Okay. And the last question in the chat so far, is your implementation available somewhere?
Not yet, but it will be once we have submitted the paper. So sometime within the next month, it should be available.
All right, thank you. Are there any other questions from the audience? In the meantime, let me remind you that we are on break next week, and we'll be back on October 23rd with Daniel Kuhl. Yes, there's a question. 1 second, we'll give you the right to use your microphone.
Hello, I wanted to just understand how often do you have these presentations and how we could also participate and deliver any presentations which are related to OR. So if you could just walk us through the process on that.
We don't have an official process for speakers, but we have the young seminars 1 to 2 times every semester or every season. Any other questions? No, that seems to be it. Thank you so much to our 3 speakers, and we'll be back on October 23rd.
Okay, thank you to everyone.
Thank you.
Thank you.
Thank you.
Bye.